November 3, 1942, Naval Air Station Puxent River, Maryland, Lieutenant Commander Thomas Blackburn peered through binoculars as the ninth prototype Corsair began its test dive from 18,000 ft. The aircraft, designated XF-4U-1, had already claimed the lives of two test pilots due to structural failures. Now it was about to either prove 3 years of metallurgical innovation or reveal that VA's claims about indestructible aluminum were fiction. The Corsair plunged like a stone, its iconic gull wings cutting through the air. At 12,000 ft, the airspeed indicator hit 350 mph. By 8,000 ft, it reached 400 mph, speeds at which the wings should have torn off. Every engineer at Wright Field had calculated the same outcome. No aluminum frame could survive such torsional stress in a near-vertical dive. Metal would fatigue, fracture, fail, yet the wings held. Blackburn lowered his binoculars. The Corsair pulled out of its dive at 4,000 ft, climbing smoothly and intact. Somewhere in the wing structure lay an alloy that, according to 1938 metallurgical theory, shouldn't exist, an alloy born from 4 years of development, 17,000 hours of testing, and a complete rethinking of how aluminum crystals could be manipulated under heat and pressure. The question wasn't whether the Corsair could dive faster than a Wildcat, a Hellcat, or a Zero. The question was how a metal lighter than steel could withstand forces that destroyed every comparable fighter in the Pacific. The answer was not in the inverted gull wing or the massive Pratt & Whitney engine, but in the molecular architecture of aluminum alloy 24ST, an impossible material created at Alcoa's New Kensington Works in Pennsylvania. This was the aircraft that would eventually shoot down 2,100 Japanese planes, more than any other Allied fighter. But in November 1942, it was still experimental, unproven, suspect. The Navy demanded numbers, evidence that VA's claims about structural integrity weren't fantasy. They needed to understand how an alloy designed for civilian transport could survive combat loads no peacetime engineer had imagined. The metallurgist behind it, 34-year-old Francis Fra at Alcoa, would never fly a Corsair or receive public recognition for solving the problem that had killed early test pilots. Yet every Corsair that dove on a Japanese destroyer, every pilot who endured 9 Gs in a turning fight, every Marine who landed a damaged fighter with wings intact, owed their survival to Fra's decisions on crystal grain size and heat treatment in 1937. The story of this impossible alloy begins not with pilots or victories, but with the challenge of making aluminum strong enough to replace steel without weighing down the aircraft. In 1937, when VA aircraft began designing what would become the Corsair, Navy specifications seemed absurdly contradictory. They wanted a carrier-based fighter capable of 400 mph, armed with 50 caliber guns with enough range to escort bombers deep into enemy territory and structurally sound enough to survive terminal velocity dive attacks. Every requirement conflicted. Speed demanded light, streamlined construction, heavy armament added mass. Extended range required more fuel, more weight. Structural integrity for high-speed dives demanded reinforcement, further increasing weight. The equation was unforgiving. Add weight, lose speed, reduce weight, compromise strength. Most American designers considered these specifications impossible. The problem centered on the wings. At 400 mph, aerodynamic loads exceeded anything seen in carrier aircraft. Pressure differences between upper and lower wing surfaces created torsional forces capable of twisting a wing until its internal structure failed. Conventional aluminum alloys, primarily 17ST, had tensile strength around 38,000 psi, enough for 300 mph dives, catastrophically insufficient for 400 mph. Steel could handle it, but a steel-winged fighter would weigh 7,000 lbs empty, far too heavy for carrier operations. VA's chief engineer, Rex Beasel, understood the dilemma. He designed the Corsair's inverted gull wing partly to solve landing gear geometry, allowing shorter, lighter gear while maintaining propeller clearance. Yet the gull wing created additional stress at the wing fuselage junction, exactly where the structure was weakest. Beasel needed an aluminum alloy with tensile strength near 55,000 psi, 50% stronger than any aluminum in production. It had to maintain strength under thousands of carrier landings, hundreds of combat maneuvers, and continuous vibration from a 2000 THP engine, resist salt corrosion, survive temperature extremes, and remain sound after battle damage. No such alloy existed. Francis Fra had spent 12 years at Alcoa, studying how metallic crystals respond to stress. Aluminum, one-third the weight of steel, had only one-fifth its strength. The key was atomic arrangement in crystalline matrices during solidification. Pure aluminum was almost useless structurally, but alloyed with copper, magnesium, manganese, or silicon, its crystal structure could be transformed. The challenge, which elements, in what proportions, processed at which temperatures and durations, would produce the strongest material. By 1937, Fra's team developed alloy 24ST, aluminum with 4.4% copper, 1.0% magnesium, and 0.0% manganese. Proper heat treatment, controlling how copper atoms distributed in the aluminum lattice, gave it remarkable properties. 24ST aluminum achieved a tensile strength of 64,000 psi, surpassing even B-Cell's most optimistic expectations. But tensile strength was only one factor. Fra had to ensure the alloy maintained that strength under cyclic loading, repeated stress that caused microscopic cracks to spread through the metal's crystal structure. He needed the material to fail gradually, giving pilots visible warning before catastrophic fracture. Testing was exhaustive. Fra's lab subjected aluminum samples to millions of stress cycles, simulating years of carrier operations in just months. They tested extremes of temperature and humidity, exposed samples to salt spray mimicking Pacific conditions, and deliberately introduced scratches, dents, and simulated bullet holes to see if cracks would propagate under load. The results were extraordinary. Properly heat-treated 24ST aluminum resisted fatigue better than any previous alloy. It bent under extreme loads before breaking, giving clear visual signs of impending failure. It maintained strength from 65° AED to 160° AED, resisted crack propagation even when damaged, and could be formed into the complex shapes B-Cell's wing design required, using conventional stamping, riveting, and assembly techniques. Fra published his findings in 1938, and aircraft designers took notice. VA engineers contacted Alcoa immediately. By March 1938, when VA received the Navy contract for the Corsair prototype, 24ST aluminum was specified for the wing spars, the critical load-bearing structures determining whether the aircraft survived high-speed dives. The first Corsair prototype, XF4U-1, flew on May 29, 1940. Test pilot Lyman A. Bullard Jr. pushed it to 405 mph in level flight, faster than any American fighter to date. The Navy was thrilled. VA seemed vindicated. The Corsair appeared to meet every impossible specification. Then the wings began failing. During dive tests at Naval Air Station Anacostia in late 1940, the second prototype's starboard wing fluttered at 370 mph. Lieutenant Roger Hedrick immediately reduced the speed and leveled off. Post-flight inspections revealed stress cracks propagating from rivet holes in the wing's lower skin panels. Engineers were stunned. The wings were built to Fra's 24ST specifications, with meticulous heat treatment and Boeing standard riveting. Yet cracks appeared after just 43 test flights. Investigations uncovered an unanticipated problem. The Corsair's massive 18F diameter propeller, powered by a 2,500 AHP Pratt & Whitney R2800 engine, generated vibrations that resonated with the wing panel's natural frequencies. At certain speeds, especially in high-power dives, vibration amplitude increased exponentially. Despite its tensile strength, the aluminum skin flexed microscopically with each vibration cycle, initiating cracks around rivet holes after thousands of cycles. Fra had anticipated fatigue failure in testing, but laboratory vibration was constant. The Corsair's propeller created complex, variable patterns. VA responded by redesigning the wing structure. Engineers added additional stringers to stiffen skin panels, shifting resonant frequencies away from propeller vibrations. They increased skin thickness in high-stress areas from 0.04 in to 0.05 in, and revised riveting patterns for more even load distribution. These changes added 63 lbs to empty weight, reducing top speed by about 4 mm and rate of climb by 200 ft, but prevented catastrophic failure. By March 1941, after 9 months of redesign, the Corsair returned to dive testing. Engineers deliberately exceeded Navy specifications. Test pilots dove from 20,000 ft, exceeding 430 mph before pulling out. The wings flexed under extreme aerodynamic loads but held. The 20-forced aluminum performed as FRA predicted, absorbing stress through controlled deformation rather than brittle fracture. Its engineered crystal structure allowed microscopic slip planes where atomic layers slid past each other, distributing loads instead of concentrating them at failure points. Proving survival in test dives was one thing, surviving combat was another. Combat imposed high-speed dives, violent maneuvers, rapid altitude changes, and battle damage from Japanese fire. The Corsair had to endure more than peacetime tests. It had to survive the chaos of aerial combat, where pilots pushed limits to survive. The first combat-ready Corsairs reached Marine Fighter Squadron VMF 124 at Henderson Field, Guadalcanal, on February 12, 1943. Commanded by Major William E. Gizzi, the squadron received 17 F-4U-1s to replace aging F-4F Wildcats. Pilots, veterans of brutal combat against Zeros, approached the new aircraft cautiously, skeptical yet hopeful. The Wildcat had saved lives despite being outclassed, outturned, outclimbed, and outperformed at higher altitudes by the Zero. Americans survived by exploiting the Wildcat's superior diving speed and structural strength, striking quickly and escaping before pursuit. The Corsair promised 430 tiros in a dive. Pilots doubted it. First Lieutenant Kenneth A. Walsh, a 7-kill Wildcat veteran, recalled his first impressions. The aircraft seemed too big, heavy, and complicated. Cockpit visibility was poor, landing gear stiff, but the speed was extraordinary. In level flight, they could reach 375 mph. The airspeed indicator would pin at 450, and the Corsair would still be accelerating. The squadron's first major engagement came on May 13, 1943, during a Japanese bombing raid on shipping in Iron Bottom Sound. 50 Japanese bombers, escorted by 30 Zeros, approached Guadalcanal at 23,000 ft to VMF 124s. Corsairs intercepted at 25,000 ft, diving out of the sun in pairs. Walsh's combat report that evening described the action. I made my first pass at approximately 430 mph indicated airspeed, fired a 3-second burst into a Betty bomber, observed strikes on the left engine, continued my dive to 15,000 ft, pulled out, and climbed back to altitude. The wings never showed any stress. I repeated this attack profile 3 more times during the engagement. Total dive time exceeded 90 seconds at estimated speeds of 450 mph. The ability to sustain such dive speeds while continuing to accelerate fundamentally changed tactics. Corsair pilots could dive away from any Japanese fighter, build separation, climb back, and re-engage on their terms. The Japanese couldn't follow. Zero fighters attempting to match Corsair dive speeds experience catastrophic structural failures. Japanese ace lieutenant Saburo Sakai, with 64 confirmed victories, later wrote in his 1957 memoir, "The American fighter dove away from my attack at a speed I could not match. When I tried to follow, my Zero began shaking violently. The controls became heavy. I knew if I continued, the wings would separate. I had to let him escape. This happened repeatedly. The Americans could dive away whenever they chose. We could not stop them." The structural advantage was no longer theoretical. It was operational. Between February and December 1943, Marine Corsair squadrons in the Solomon Islands achieved a kill ratio of 11.3.1. For every Corsair lost, 11 Japanese aircraft were destroyed. Much of this advantage came from controlling engagement geometry through superior dive performance. What pilots experienced as confidence in their aircraft's structural integrity was actually a molecular battle occurring inside the Corsair's wings during every high-speed dive. At 450 mph in a near-vertical dive, aerodynamic pressure on the wings exceeded 14 psi differential, across a 314 square foot surface area, about 600,000 lb of force attempting to tear the wings from the fuselage. The 20-forced aluminum spars resisted this through material properties not fully understood by metallurgists until the 1950s. Copper atoms distributed in the aluminum lattice created precipitation hardening. During heat treatment at Alcoa, the alloy was heated to 930 degrees, held 6 hours, then rapidly quenched. This forced copper atoms into solution. The material then aged at room temperature for 4 days, forming microscopic clusters called Guinier-Preston zones. These clusters obstructed dislocation movement within the crystal structure, resisting deformation and requiring much higher stress to bend permanently. This explained 24C aluminum's 64,000 psi tensile strength, nearly twice that of pure aluminum. Frey's true innovation was controlled failure behavior. The alloy was designed to deform visibly before catastrophic fracture. When stress exceeded yield strength, aluminum bent permanently, creating visible wrinkles in skin panels, warning pilots and ground crews before failure. By contrast, Japanese Zero fighters used extra super duralumin, ESD, developed by Sumitomo Metal Industries. ESD had similar tensile strength, 8-hour 60,000 psi, but failed differently. Brittle, prone to sudden fracture without warning. Cracks propagated internally, causing catastrophic failure, often without visible signs. This explained why Zeros broke apart in high-speed dives while Corsairs survived. Both alloys had similar strength, but 24C aluminum bent and wrinkled, dissipating energy, while ESD cracked and failed suddenly. By mid-1943, Japanese intelligence had detailed Corsair performance from captured aircrew and wreckage. Engineers studied the aluminum, understanding that American metallurgists had superior material properties, but Japan lacked the production, capacity, quality control, and research infrastructure to replicate Alcoa's achievements. By 1944, the disparity affected Japanese tactical doctrine. Imperial Japanese Navy fighter tactics manuals, revised March 1944, explicitly warned pilots not to follow American fighters into high-speed dives. Their aircraft simply couldn't match American structural strength. This disparity extended beyond metallurgy into industrial capacity. Alcoa's New Kensington plant, producing 24ST aluminum, operated 24 hours a day, employing 12,000 workers across 3 shifts, producing roughly 40 million pounds of aircraft-grade alloy annually. Quality control was absolute. Every batch tested for composition, tensile strength, and fatigue resistance before shipment. Japan's entire aluminum industry, by contrast, produced about 120 million pounds annually across all grades, military and civilian combined. Of this, only about 30% met aircraft-grade specifications. Japanese aluminum production was limited by scarce bauxite supplies, requiring imports from the Dutch East Indies, compounded by inadequate electricity and outdated refining equipment. Aluminum production demanded massive power and modern facilities, which Japan lacked. More importantly, Japanese metallurgists didn't have access to the foundational research that enabled Frey's breakthroughs. Alcoa had invested millions in the 1930s, building laboratories, hiring physicists and materials scientists, and systematically studying aluminum crystal structures under stress. Japanese producers, primarily Sumitomo and Mitsubishi, worked with far smaller budgets and less advanced equipment. They could analyze American samples recovered from crashes, but understanding composition didn't reveal heat treatment, protocols, aging procedures, or quality control standards. This created an unbridgeable gap in material performance. By late 1944, American fighters routinely operated at speeds and dive angles that would destroy Japanese aircraft. Marine Corsair pilot, First Lieutenant Robert M. Hansen, who would achieve 25 confirmed kills before his death in February 1944, described the advantage in a letter to his family. "We can dive away from anything they have. When they try to follow, their wings fold. We've seen it happen dozens of times. They're brave, they're skilled, but their planes can't take the punishment ours can." The statistics reinforce this. Between January and December 1944, Corsairs in the Pacific achieved a kill-to-loss ratio of 14.6.1. For every Corsair lost in air combat, American pilots destroyed nearly 15 Japanese aircraft. Much of this advantage came from controlling engagements through superior dive performance, diving to attack, diving to escape, climbing back, and repeating the cycle almost at will. Japanese losses were catastrophic. By September 1944, the Imperial Japanese Navy had lost approximately 60% of its trained carrier pilots in combat against American fighters capable of outdiving, outrunning, and surviving punishment that Japanese aircraft could not. The Zero, once the Pacific's most feared fighter, became a death trap against Corsairs, Hellcats, and Lightnings, exploiting their structural advantages. Surviving Japanese pilots later described feeling hunted and unable to escape or effectively engage. Japanese defeat was not due to inferior flying skill, but superior American metallurgy, industrial capacity, and systematic pre-war research. Francis Fraw never saw a Corsair in combat. He spent the war at Alcoa's New Kensington plant, managing aircraft-grade aluminum production, solving quality control issues, and developing new alloys. His work was classified, and his contributions unknown outside metallurgists and military procurement circles. By 1945, 24ST aluminum underpinned most American military aircraft. Beyond the Corsair, it was used in P-51 Mustangs, B-29 Superfortresses, C-47 transports, and dozens of other designs. In 1944 alone, the U.S. produced 96,000 aircraft, nearly all using alloys Fraw developed or improved. Post-war analysis revealed Fraw's achievement. The Army Air Force's 1946 Technical Data Digest reported catastrophic structural failures in American aircraft averaged 0.37%, fewer than 4 per 10,000 Tawan, excluding combat damage or pilot error. Japanese aircraft, by contrast, experienced structural failures exceeding 25%, nearly 7 times higher. This difference translated into thousands of American pilots surviving encounters that would have killed them in inferior aircraft. Every high-speed dive without wing failure, every hard carrier landing without gear collapse, every extreme maneuver without structural breakup reflected Fraw's contribution to victory. Fraw received the Army-Navy E Award in 1944 for wartime production excellence, a certificate, and a small ceremony at the New Kensington plant. He continued at Alcoa post-war, eventually becoming director of research, publishing 73 technical papers on aluminum metallurgy, and training a generation of materials scientists who developed modern aluminum-lithium alloys. He died in 1968, largely unknown outside metallurgical circles. His obituary in the Journal of the American Chemical Society mentioned his contributions to aircraft aluminum in a single sentence. There were no memorials or public recognition of his role in enabling the Corsair, Mustang, Superfortress, and Allied victory in the Pacific. Among materials scientists and aircraft designers, Fraw's legacy was profound. His principles, controlled heat treatment, precipitation hardening, engineered failure behavior, became foundational to modern aerospace materials. Every commercial airliner, military jet, and spacecraft uses aluminum alloys developed according to the principles Arra pioneered in the 1930s. The Corsair itself became legendary, the most successful carrier-based fighter of World War II, with 2,040 confirmed air-to-air kills. Production continued through 1952, totaling 12,571 aircraft. Corsair served in the Korean War, achieving additional victories and proving the airframe's structural integrity a decade after initial deployment. The aircraft's success was fundamentally enabled by decisions made in a Pennsylvania laboratory in 1937 by a metallurgist who understood that strength without controlled failure was useless, that superior performance required predictable material behavior under stress, and that winning wars required winning the industrial and technological competition years before combat began. Corsair pilots trusted their aircraft's structural integrity. They knew they could dive at speeds that would destroy enemy fighters and trust that the wings would hold under forces exceeding 9 Gs. That trust was built on 24ST aluminum, on Francis Fraw's understanding of crystal structures and precipitation hardening, on Alcoa's quality control and production capacity, and on an American industrial system that invested in fundamental research when it seemed disconnected from immediate military needs. The final Corsair rolled off VA's production line in December 1952, 10 years and 7 months after the first combat-ready aircraft reached Guadalcanal. By then, the Corsair had accumulated a combat record unmatched by any other American fighter. 64,651 sorties were flown, 2,140 enemy aircraft destroyed in air-to-air combat, with thousands more destroyed on the ground, and a loss rate lower than any comparable fighter in the Pacific theater. The Corsair's structural integrity, the characteristic that enabled its tactical dominance, never wavered. Maintenance records from Marine squadrons show major structural failures, wings separating from fuselage, catastrophic airframe breakups in flight, occurred at rates below 0.2% of total flight hours. This was extraordinary given the punishment Corsairs absorbed, carrier landings at sink rates exceeding 13 mph, combat maneuvers at G-forces causing pilots to experience vision graying, dive speeds over 460 mph, and battle damage from Japanese anti-aircraft fire and fighters. By 1945, Japanese pilots flew aircraft stored for years, aluminum weakened by corrosion and poor maintenance, further degraded by time and environmental exposure. American pilots reported encountering Japanese fighters that broke apart during moderate G maneuvers. Wings failing under loads, Corsairs routinely absorbed. Post-war inspections of Japanese manufacturing facilities confirmed wartime metallurgical intelligence. Japanese aluminum was inconsistent, poorly heat-treated, and produced with quality control far below American standards. The gap wasn't just technological, it reflected fundamental differences in industrial philosophy, research investment, and manufacturing culture. Lessons from the Corsairs' development shaped American aerospace engineering for generations. Superior materials enable superior performance. Methodical research pays dividends beyond immediate costs. Engineered failure behavior matters as much as ultimate strength. Modern fighters capable of Mach 2+ speeds and 12G maneuvers use aluminum-lithium alloys and titanium composites developed according to principles Francis Fra established. The F-18 Super Hornet, descendant of carrier-based fighters like the Corsair, uses materials whose development traces directly to 1930s-40s metallurgical breakthroughs. The Corsair's legacy extends beyond materials to strategic understanding. Its success demonstrated that wars are won in laboratories and factories years before combat begins. Technological and industrial superiority determine outcomes regardless of tactical skill or individual courage, and investment in fundamental research provides decisive advantage. Commander Thomas Blackburn, who observed the first high-speed dive at Patuxent River in November 1942, later wrote that when he saw the Corsair pull out intact, he knew American industry had solved problems Japanese engineers hadn't fully understood. The ocean wouldn't be Japan's. The sky wouldn't be Japan's. Victory would go to the nation that could build aircraft capable of diving at 450 meters without wings tearing off. That capability rested on 24ST aluminum, Francis Fra's research, Alcoa's production capacity, and an industrial system Japan couldn't match. Recordings of combat radio traffic from Corsair squadrons, preserved in the National Archives, capture the confidence American pilots had in their aircraft. They dove without hesitation, pulled crushing G-forces without concern, and trusted their wings absolutely. That trust was earned in Pennsylvania laboratories in 1937, in VA factories in 1941, in dive tests at Patuxent River in 1942, and in thousands of combat encounters where the aircraft performed exactly as promised. The impossible alloy that allowed Corsairs to dive at 450 mph without wings tearing off was not impossible. It was the product of systematic research, industrial investment, and metallurgical understanding that one nation possessed and another could not replicate. The difference, aluminum crystal structures and heat treatment protocols, determined who controlled the Pacific sky and ultimately who won the war. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.